So now let's focus our attention to Bernoulli distribution. It is the simplest discrete probability distribution function. So Bernoulli distribution, it actually essentially represents a single experiment or a trial that has only two outcomes. There are only two possible outcomes. Either you can succeed or you can fail. Generally, your success is denoted by 1 and your failure is denoted by 0. So if your probability of success, okay, let's say you denote your probability of success by P. So let's say your P equal to 0.6. In other words, your probability of success is 60%, then your probability of failure is going to be 1 minus P. This would be in this case 0.4. So 40% chance that you're going to fail. Now, the probability mass function, your PMF, is denoted by this expression right here. Okay, this expression is telling you that your probability of x equal to 1 is P, and the probability that your x equal to 0 is 1 minus P. Here, my x, the capital X, is your random variable. It can take only two values, 0 or 1. This is a pictorial representation of this PMF. So this is essentially saying that your probability of x equal to 0 is equal to 1 minus P, and probability of x equal to 1 is equal to P. Now, some of the use cases of this particular PMF is, for example, in your coin toss. So, if you toss a coin, you can either get a head or you can get a tail. Maybe you give a test. In your test, you can either pass or you can fail. Likewise, an email comes to you. It can be a spam or not a spam. How about manufacturing? Well, you can get a defective piece or not a defective piece. So these are very simple use cases of Bernoulli distribution. Suppose you flip a fair coin once. Fair basically means that it's a 50-50 chance that you can get either a head or you can get a tail. What is the probability mass function? In this case, there are only two outcomes. You can either get a head or you can get a tail. So let us say we denote our success as head. Okay, my head, which is 1, I'm going to denote that as a success. And likewise, my failure, I'm going to denote that as a tail, which is 0. So here my random variable x can only take two values, 0 and 1. 0 would mean tail, 1 would mean head. So for this fair coin, my PMF is going to be P of x equal to 1, which is the probability that you get a head, is equal to 0.5, and likewise the probability that you get tail is equal to 0.5. So this is my PMF right here, and I can represent this pictorially like this. So this is saying, essentially this is saying that the probability of my tail is equal to 0.5. So this height right here, okay, this height is 0.5, and this height right here is also 0.5. So this is the probability of head. Let's say you're provided a data set that contains email received and whether it is a spam or not. This is the data set that's provided to you. And in this case, let's say you can tell that email E3 is a spam. It says Y means spam and no means not a spam. So email 5 is not a spam. So let X be a random variable that indicates whether that email that you received is a spam or not a spam. So assuming that we can calculate the probability that an email is a spam or not from this data set, what is the PMF of X in this case? So here, my X is a random variable that indicates whether my new email is a spam. Let's say I use 1 to denote it's a spam or it's not a spam. So I'm using 0 to denote not a spam and 1 to denote that it is a spam. So my X in this case is going to be 0, comma 1. By looking at the data, okay, by looking over here, you can see that the probability of spam is going to be 4 over 7 because there are 4 emails that are spam. 1, 2, 3, and 4. These 4 emails are spam. That's why you get 4 over 7. 7 because their total number of emails is spam. On the other hand, probability that not a spam is going to be, you count how many of them are not a spam. You have this one, not a spam, right? This one is not a spam, not a spam, and this one is not a spam. So you have 3 of them that is not a spam. So the probability of x equal to 0, in other words, not a spam, is 3 over 7. You can actually represent this pictorially like this. So probability of 0, okay, which is not a spam, is going to be 3 over 7. So the height of this is 3 over 7, and the height of 1, which is probability of a spam, is going to be 4 over 7. Suppose you have an AI system, okay, it can classify a single image as either a cat or not a cat. And let x be equal to 1 if the AI correctly classifies the image. On the other hand, let x equal to 0 if it misclassifies. So suppose what's given to you is that the probability that your AI correctly classifies an image, the probability is 0.9. It's 90% chance that it classifies the image correctly. What is the PMF? That's your first question. The second question is, if we repeat the classification process twice, okay, once more, and they are both are independent, what is the probability that both classifications are correct? Well, let's start question number one first. I know my probability of x equal to 1. In other words, probability that your AI classifies the image correctly is 0.90. That's given to me. So the probability that your x equal to 0, that means it misclassifies, is going to be 1 minus zero point 0.9, and the answer comes out to be zero point 0.10. So this is my probability of misclassifying. So my PMF is denoted with this expression right here. All right, now I can represent this pictorially like that. So the probability of misclassification, in this case, probability of 0 is equal to zero point 0.1, and the probability of 1, which is the probability of correct classification, is zero point 0.9. Now, the probability that both classifications are correct, okay, in other words, the probability that your x equal to 1 and x equal to 1 in both trials, in both experiments, is going to be equal to probability of x equal to 1 multiply by probability x equal to 2. Well, in this case, we are able to multiply because we know our processes are independent. This is only applicable if your processes are independent, and that's given to us. Multiply zero point 0.9 by zero point 0.9, and the answer is 0.81. So it's 81% chance that both classifications are correct.